Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So today we are going to do the part 2 of equilibrium chapter, in which we are going to discuss homogeneous and heterogeneous equilibrium and applications of KC. Okay, so yes, now let's get started. And one more thing, please join our WhatsApp channel, link is there in the description section. So this will help you to get access to all our PDF notes, mock test and solutions. Okay, so yes, now coming to this chapter, how we are going to cover, that is 4 parts will be there. So in first part we are going to cover we'll be covering equilibrium in physical processes. This we have already done. Then this is also, these all are covered. And in today's lecture we are going to discuss homogeneous equilibrium, heterogeneous equilibrium, applications of KC and stoichiometric coefficients and KC. Okay, this is going to be a very important thing. Next, in the next class we will be discussing factors affecting equilibria, ionic equilibrium in solution, acids, bases and salts. Okay, and then ionization of acids and bases. In the last class we will be discussing buffer capacity or buffer solutions and solubility product. So coming to today's class, year wise weightage, you can expect 1 to 2 questions from this particular chapter. And in today's class we are going to discuss these topics. Now coming to homogeneous equilibrium. So homogeneous equilibrium means the reactants and products should be in the same phase. Okay, so for example, you can see I am writing this reaction, N2 plus H2 gives NH3. Okay, N2 plus H2 gives NH3, and you can see nitrogen, hydrogen and NH3 all are in the gaseous phase, right? So these type of reactions are called as homogeneous equilibrium. Similarly, you can see here Fe, this is also aqueous and this is also aqueous, right? So this tells you that all the reactants and products are in the aqueous phase, and that is why this is an example of homogeneous equilibrium. Okay, now what happens if the reaction is in the gaseous phase? Okay, then how we write the equilibrium constant? If the reactants and products are in the gaseous phase, okay, in that case Kp will be equal to Pa to the power of A, Pb to the power of B, Pc to the power of C, Pd to the power of D. Now what is this reaction? This reaction should be like this: Cc plus Dd, okay, gives AA plus Bb, right? So now these all are in the gaseous states. Okay, now if you see Pa to the power of A, Pb to the power of B divided by Pc to the power of C and Pd to the power of D, these are the stoichiometric coefficients raised to the power of their stoichiometric coefficients. A, B, C, D are the pressures given. Okay, next if you see what is the relation between Kp and Kc, this is very important formula here. Kp is equal to Kc into RT to the power of delta Ng. Now what is delta Ng here? Delta Ng is equal to number of gaseous moles of products minus number of gaseous moles of reactants. Okay, products minus reactants. And one more important thing, here R and T is there. Okay, that is your R is your universal gas constant and T is temperature. Okay, so this is the relation between Kp and Kc. Kc is the equilibrium constant when the concentrations are taken. Kp is the equilibrium constant when the reactants are in the gaseous state, and we take pressure as the term. Okay, what is this? Pa, Pb, Pc, Pd, these are all the pressure term, right? Pressures. Clear? Now let us move towards heterogeneous equilibrium. So in heterogeneous equilibrium, reactants and products are in different phases. Okay, example you can see calcium carbonate, if you heat it we get calcium oxide and carbon dioxide gas. So now here one very important thing, if I want to write Kc, okay, what will be the formula? I will be writing CO2 concentration into CaO concentration divided by CaCO3 concentration, right? And here is a trick that you should, or here is a thing that you should know, that is what is that? Yeah, that is your CaO and that is the concentrations. Okay, concentration of pure solid, okay, or liquid is taken as 1. Concentration of pure solid or liquid is taken as 1. Okay, now if you see this one Kc, we can write it CO2, that will be only CO2, right? This one will be 1 and this one will be 1 because it is what? Pure solid. Okay. Next we have, sorry, one second, I erased the whole thing. Okay, once again I'll write concentration. Okay, concentration of pure solid, okay, or liquid is taken as 1. Okay, now if you see calcium carbonate, okay, what I'll write here, K will be equal to calcium oxide concentration divided by carbon dioxide, multiplied with CaCO3, right? Now these all are pure solids, right? This is okay, so calcium oxide and calcium carbonate are pure solid, so we can just consider that their concentration is taken as 1. So what I'll get, Kc will be equal to concentration of CO2, and since it is a gas, I can also write Kp is equal to P of CO2, right? Now similarly, if I want to write for K, for this one, it will be what? NiCO4, okay, divided by Ni into CO to the power of 4. Clear? So now if you see here, nickel is a solid, right? You can eliminate that. So I can write this one as NiCO4 divided by CO to the power of 4. Okay, and since it is gas, we can also write in the form of Kp, right? Kp is equal to P times, okay, NiCO4 divided by P times CO to the power of 4. Okay, so that is the expression of Kp. Next, coming to applications of Kc, this is very important. Before that, we should know some features of Kc. Okay, so first of all, Kc is always applicable only when the concentrations of the reactants and products have attained a constant value at equilibrium state. Okay, when the reaction has already reached equilibrium, at that time whatever concentrations or pressures are there, that will affect your K value. Okay, second thing, it is independent of the initial concentration. So I have explained this in the last class also. If you start the reaction with 1 mole and at equilibrium it is 0.5, or you start the reaction with 2 mole and at equilibrium it will be same 0.5, right? So the K value will not be affected by the initial concentration. Next, coming to equilibrium constant is temperature dependent. Okay, it will depend on the temperature. At a particular temperature for a particular reaction, K value is constant. If you change the temperature, K value will also be changing for the same reaction. Clear? So, and now coming to the applications, the first application is predicting the extent of reaction. Okay, we'll explain what is this. Second application is predicting the direction of reaction. This is very important. Next, calculate the equilibrium concentrations and calculate delta G. Okay, these are the 3 applications. Let us move towards the first application, that is predicting the extent of reaction. Now here there is something, if the K value, okay, is coming greater than 10 to the power of 3, okay, K value is greater than 10 to the power of 3, that means the reaction is product favored. Product favored. Clear? Next one, if your Kc value, okay, is less than 10 to the power of minus 3, okay, that means the reaction is reactant favored. Reaction is reactant favored. Means, what do you mean by reaction is product favored? That means concentration of reactants will be less than concentration of products when at equilibrium. Okay, if you see, once the reaction has reached and if you are checking the concentration of the reactant in products, the product concentration will be more than the reactant concentration. Now here what do you mean the same thing, that here the concentration of reactant will be greater than the concentration of product when at equilibrium, right? So reactant concentrations will be more once the reaction has reached equilibrium is attained, and then you measure the concentration of the reactants and products. Reactant concentration will be more than the product concentration. Okay. Next one is the value of Kc should be 10 to the power of 3. Okay, but if the value like 10 to the power of 3 and 10 to the power of minus 3, okay, if the value lies between this one, okay, I put the wrong sign, yeah, so it is like between 10 to the power of 3 to minus 3, then we can say that the reactant and product concentration is comparable. Okay, that means product concentration and the reactant concentration will be equal or almost equal, may not be, but not be very different from each other, but here it will be much difference. Okay. Next, coming to the second second application, that is direction of reaction. This is very important. From here you can expect questions. Now suppose a reaction is there, AA plus BB, okay, gives you CC plus DD. Okay, there is something called as Q, okay, or we can call it as reaction quiescent. Okay, reaction quiescent. Now what is this reaction quiescent? The formula of reaction quiescent is same as that of equilibrium concentration formula. So here I can write this as concentration of D to the power of D, concentration of C to the power of C, concentration of B to the power of B, and concentration of A to the power of A. Right. Now if I want to calculate Kc here, okay, the same thing I'll write D to the power of D, B to the okay, so we have C to the power of C, B to the power of B, and A to the power of A. Right. Now if you see this one, the formula seems very same, right? Both of them are same, but what is the difference? Here the concentration that you have taken are all equilibrium concentrations, means when the reaction has already attained the equilibrium, but these concentrations at any time t, it may be at equilibrium, it may not be at equilibrium, it may be before equilibrium, after equilibrium, it can be any time concentration. If you are taking and calculating the product by reactant concentration, that is called as reaction quiescent. If you are taking the concentrations when the reaction has already attained equilibrium and then you are putting the values, that is called as equilibrium concentration. Okay. Now coming to this one, how it will help you to predict the direction of reaction. Now see, if the Q value, okay, is greater than K value, in that case what will happen? Reaction will proceed in backward direction. Okay, if so, there can be three conditions, right? Q can be greater than Kc, Q can be less than Kc, and Q can be equal to Kc. So now if Q is less than Kc, then reaction will go in forward direction, and if Q is equal to Kc, that means the reaction is already at equilibrium. So in this way we can predict the direction of reaction. If Q, suppose this is equilibrium, right, and the Q value is somewhere here more than K value, so reaction has to proceed in the backward direction to match the K value. If Q value is less than K value, then reaction has to go in the forward direction to match the K value. If Q and K are equal, then the reaction is already at equilibrium. Okay, that is how you can find these values. Next, coming to the third one, that is relationship between delta G and K. So delta G is nothing but your gives free energy. Okay, so what is the relation here? Write down this formula. Delta G is equal to minus 2.303 RT log of K. Okay, where the terms are like this: R is your gas constant, R is gas constant, T is temperature, and K value is equilibrium constant. Okay, clear? So these are the things that you should remember, and this formula is very, very important. You can expect question from this formula. Okay, so what is delta G here? Again, delta G is nothing but gives free energy. Delta G is gives free energy. Clear? Okay. Now what we are going to do, so three applications of K is clear. First one is to predict the extent of reaction. If it is more than 10 to the power of 3, it is more towards product. If it is less than 10 to the power of minus 3, it is more towards the reactant. If it is between 10 to the power of plus 3 and 10 to the power of minus 3, then the reactant and product concentration will be almost equal or towards nearly equal to each other. The second one is to predict the direction of reaction. In this, we are calculating the Q value or the reaction quotient. In that, you take concentrations at any point of time. Okay, and then when you take you calculate the Q value and compare it with the K value. If it is more than Q value, like if Q value is more than K value, then reaction has to proceed in backward direction. If Q is less than K value, reaction has to proceed in forward direction. If Q is equal to K value, reaction is already at equilibrium. I hope that is clear. The next one is your relation between delta G and K. This is the formula. Delta G is equal to minus 2.303 RT log of K. Okay, fine. Now what we are going to do, now we will see in the next topic, that is stoichiometric coefficients and Kc. From here also questions are asked, very important. So I will be telling you here also three cases. First one, if a reaction is there, A is in equilibrium with B. Okay, and it's okay, let me give the heading and write. Okay, the first case is if you inverse, I think it is there, one second. Okay, so now the first thing, if the reaction is reversed. Okay, if a reaction is reversed, how the K value will change. Now example, let us see. If you have A gives you B plus C, okay, and its K value is K1, and if you have B plus C is giving you A, then what you have done exactly, you have reversed this reaction, right? B plus C has changed to A, just reversing of reaction. In that case, what will be K dash value? It will be the inverse of this one, 1 by K1. Okay, 1 by K1. A giving you B plus C, that is K1, and if you reverse the reaction, B plus C giving you A, that is K dash is equal to 1 by K1. Okay, next what is there? If the reaction is multiplied by N. Okay, so suppose you have A giving you B plus C, okay, and you have NA, NB and NC. Okay, sorry, one second. What we will do is, so this reaction is there, the same reaction, and its equilibrium constant is K1. Now you multiplied N with that, so we have NA giving you NB plus NC, right? So what you have done, you have multiplied the whole equation with N. In that case, the new K dash value will be K1 to the power of N. This is very important. Many times you do mistake, you multiplied N K1. No, the number that you have multiplied here will go as a power for K1. Okay, and the next one is if reactions are added. So suppose I have a reaction, A is giving you B plus C, okay, and B plus C is giving you D. These are two reactions. This value is K1 and this value is K2. Now I have added these two reactions to give A giving you D. Right, A is giving you D. In this case, if two reactions are added, the K dash value will be K1 into K2. Okay, this is also very important. When two reactions are added, their K values are multiplied. Okay, if any reaction is multiplied with a factor of N, then the reaction, the equilibrium constant is multiplied with a factor of N or is raised to the power of N. If you reverse the reaction, then the K value is also reversed. Clear? Okay, so now that's all. Now we'll do some questions based on the concepts that we have practiced today. Okay, so let's start with the first question. So at 500 Kelvin, for a reaction A2 plus B2 giving 2AB in a closed container, Kc value is 2 into 10 to the power of minus 5. In the presence of catalyst, the reaction the equilibrium is attaining 10 times faster. Okay, the equilibrium constant Kc in the presence of a catalyst at the same temperature is. So just now we have studied that equilibrium constant can only be affected by temperature. If the same temperature is maintained, even if you use a catalyst, the K value will not change. So it will same 2 into 10 to the power of minus 5. Option number D is the correct answer here. Okay, next question number 2. Okay, 1 mole of HI is heated in a closed container of capacity 2 liter. Okay, at equilibrium, half a mole of HI is dissociated. The equilibrium constant of the reaction is? Okay, this is also very important and good question. Now first of all, if you write the reaction of or the decomposition of HI, it is like this: H2 plus I2. Okay, now you see when you started the reaction, okay, when you started the reaction at time t equal to 0, how many moles of HI was there? 1 mole of HI was there. At that time when you just started the reaction, H2 and I2 will be 0, right? Now at t equal to some point of time when the equilibrium has reached, okay, the question here says that at equilibrium half a mole of HI is dissociated. So means 1 mole, half of it has dissociated, so 1 minus 0.5, right? Now if you see here, 2 moles of HI, see 2 moles of HI is giving you 1 mole of H2, right? Then 1 mole of HI will give you how much? 1 mole of HI will give you 1/2 mole of H2, right? And then we have, but how many moles of HI has actually reacted? 0.5 moles of HI has reacted. So I can say that half mole of HI will give you 1/4 mole of H2, right? So what I will get here? 1/4, sorry, okay, so we will get 1/4 mole of H2 and 1/4 mole of I2. Okay, 1/4 mole of H2, 1/4 mole of I2. Now, so and what will be left here? Half, right? Half mole of HI is left, 1/4 mole of H2 is there, 1/4 mole of I2 is there at equilibrium. Okay, initially we had 1 mole of HI, half mole dissociated, so half mole of HI is left. Now from that half mole, half means 1/4, 1/2 mole, 1/4 went and formed H2, 1/4 formed I2. Now you need to calculate the equilibrium constant for this one. Okay, so now these are number of moles, right? But these are not concentration. So what will be the concentration of HI? Number of moles by volume. So 1/2 divided by 2, right? The volume is 2 liters, so that is 1/4. And what will be the concentration of H2 and I2? That will be 1/4/2, that is 1/8. Okay, so now we will get 1/8. Okay, let me write the first expression. We will have H2 concentration into I2 concentration divided by HI to the power of 2. Okay, now H2 concentration is 1/4, I2 concentration is 1/4, and then we have this one is H2 concentration is 1/8. Let me correct it. Yeah, this is 1/8, this is 1/8, and this one is 1/4, 1/4 square, so I can put it 2 times. Okay, so what I will get? 1/8, 1/8, so I'll get 4 into 4/8 into 8, right? So that will be, we will get 1/4 or 0.25. So correct answer is option number A here. Okay, next question number 3. The relationship between Kp and Kc is given to you. What would be the value of delta N for the reaction? So delta N, how to calculate? Delta N G is equal to number of gaseous moles of products minus number of gaseous moles of reactants, right? So number of moles of products is how much? 1 plus 1, 2, right? 2 minus 0, that will be equal to 2. Okay, so option number D is the correct answer here. Next question number 4. The reaction question QC is useful for predicting the direction of the reaction. Which of the following is incorrect? Okay, so if QC is greater than Kc, the reverse reaction is favored. Okay, that is correct definitely. If QC is less than Kc, forward reaction is favored, that is also correct. If QC is greater than Kc, forward reaction is favored, that is wrong. So option number C is the correct answer here. Okay. Next is question number 5. Given that 800 Kelvin, the concentrations are as follows: 3 into 10 to the power of minus 3, 4 into 10 to the power of minus 3, 2.8 into 10 to the power of minus 3. What is the equilibrium constant for the following reaction? I think this question I have done in the previous class also, but let us solve it once again. So the reaction is like this: N2 plus O2 gives 2NO, right? So if I substitute K value, it will be NO square, right, divided by N2 and divided by O2. So now if I write down this one, NO value is 2.8 into 10 to the power of minus 3 square, right, divided by, you have 4.2 and 3. So 3 into 4.2 into 10 to the power of minus 6. So if I solve this, we will be getting 0.622. Option number A will be the correct answer here. Okay, next this question is again very important one. Equilibrium constant K1 and K2 for the following reactions are related as. Okay, so this is this reaction value is K1, this value is K2, right? What is the relation between them? Okay, so now if you see the first reaction, NO plus half O2 gives you NO2. In the second reaction, NO2 is on the reactant side, and in the first reaction, NO2 is on the product side. That means this reaction, first what is done, reaction 1 is reversed. 1 is reversed. Okay, so if I reverse the first reaction, what I will get? NO2 gives, okay, NO plus half O2. Okay, now if this reaction is K1, if the first, this one reaction equilibrium constant is K1 and I have reversed the reaction, then what will be its K value now? It will be 1 by K1, right? Next, you are multiplying 2 to the whole equation. Okay, if I multiply 2 to the whole equation, multiply 2 to the reversed equation. Okay, so I'll get 2NO2 gives you 2NO plus O2. Okay, so now if I see this one, we will get 2 times, the reaction is multiplied by 2 times, so I will get 1 by K1 into square. Okay, 1 by K1 square will be the correct answer. So K2, which is the equilibrium constant of this reaction, is 1 by K1 square. So where I can find K2 is equal to 1 by K1 square, option number D is the correct answer here. Okay. Okay, next this question you have to try by your own. Okay, for the equilibrium CaCO3 gives CaO plus CO2, Kp value is given at 1000 Kelvin. Okay, 50 gram of CaCO3 in a 10 liter vessel is heated to 1000 Kelvin. The percentage of CaCO3 that remains unreacted at equilibrium is. Okay, you have to find the percentage of CaCO3 that remains unreacted at equilibrium. Given value of R is this one. Okay, so try this question. I'll be discussing the solution in the next class. Okay, so yes students, that's all in this particular lecture, and I hope you would have understood all these concepts. And if you have found this lecture helpful, then do not forget to subscribe the channel, and see you very soon in the next class.